Okay, thank you everyone for coming back, and glad to see so many people still out even as today we're going to be looking at, as you can see, building the planets. So we've looked so far at building up to a disk of what we call planetesimals, these 10 to 100 kilometre sized bodies in the disk around our young sun. Today we're going to be looking at the next step, so how do we go from that kind of size of object up to something the size of a planet. As I said, so far we've looked at 3 weeks ago we looked at making planetesimals. Last week we looked at those planetesimals in the solar system today before the asteroids, and we'll look at building planets today. We're then going to go on over the next few lectures to start to look at more collision processes, the kind of thing that I do in my day job, looking at the real physical processes that happen when two things collide at high velocities. I'm going to get straight into the lecture because there's a lot I want to talk about today. So as I said, we'll talk about the formation of terrestrial planets first of all. We'll talk about how we form Mercury, Venus, Earth and Mars. Then we'll look at why the outer planets are so different to the inner planets and how they form in the early solar system. And then finally, I want to just touch on some recent advances in the field. There's two models that have gained a lot of prominence in the field. One is called the Nice model and one is called the grand Tack theory. And we'll talk about those kind of recent advances along with a few other things to just give you a kind of up-to-the-minute update on the kind of ideas that we have about planet formation. So if you remember from the first two lectures, we came up with a model that explained why planets all have near circular orbits around the Sun. They all orbit in the same plane as the Sun's equator, and they all orbit in the same direction around the Sun. And we could explain all of those with our theory of the disk forming around the young Sun, collapsing from the nebula. What we didn't explain with that was why the inner planets are rocky and dense, and the outer planets are gaseous and large. That was one of the things I talked about in the first lecture, about some of the observations we can take from the solar system. We can then try and fit our model to, but we haven't yet touched on really why there is such a dichotomy between these two populations of planets. And that's what we're talking about today. So first of all, as I said, we'll talk about how we form the terrestrial planets. For the next few slides, I'll just give you a kind of brief overview of the terrestrial planets and some of their physical properties, and then we'll look at the mechanism for forming those planets. So first of all, closest to the Sun, we have Mercury, the smallest of the planets. It's around 40% radius of the Earth. It has a very high density, which is the second highest of all the planets after the Earth. But its very strong component is metal. It contains a very large metallic core, and it's possible that this core was formed in a giant impact event, stripping off some of the rocky material from the outside. But if you look at the surface of Mercury, you can also see one of the dominant features on the surface is impact craters. So you can see all over here we have lots and lots of impact craters. And even if you look at on a bigger scale, you can see here we have a large impact crater. This is the Flora Basin. This is one of the largest impact features in our solar system. It's around 1,000 miles in diameter. Next out from the Sun, we have Venus, which is similar in size to the Earth, and is generally covered in this thick, dense cloud. So we struggle then to see the surface, but if you use particular techniques, we can see through that cloud and look down onto the surface. And on the surface, we see that it's a very active surface. There is volcanic activity going on. We still have impact craters forming on the surface. But you actually notice an interesting thing about the impact craters on Venus is that there are no craters smaller than around 3 kilometers in size. And the reason for that being is that the clouds in the atmosphere stop any small impactors getting through to the surface, and so prevent any smaller craters from forming. But there's still around 1,000 craters on the surface, so it's still one of the dominant features on the surface of Venus. Next out from the Sun, we have the Earth, which is the most dense of all the planets, and as you know, it has a very active surface. We have plate tectonics, we have volcanism, we have the oceans, which do a lot of work on the surface. And all these things add up to mean that we have many fewer craters on the surface of Earth than we do on most of the other solid bodies in our solar system. We only have 182 confirmed craters, and that's mostly because of the fact that these processes all work to either mask or destroy craters that have formed earlier in the history of the Earth. Here's just a map of all the confirmed craters we do have on Earth, marked in orange. And what you'll notice is there's also a bias as to where we're discovering these craters. There's many in Northern America and Europe and Australia, and these are the kind of areas where detailed geological mapping has been done generally in the search for oil and minerals. But there's vast areas that haven't been mapped in such detail, and that's where we have less craters found. So you can imagine that actually that number, 182, could go much higher with much more detailed mapping. And also you'll notice that there are very, very few, if any, craters that we seem to see in the oceans, which again, as I said, helps to bias that number to a lower number. And then finally, for the terrestrial planets, we have Mars, which is the outermost of the terrestrial planets. It's smaller than Venus and Earth. It's only around 1/10 or 11% of the mass of Earth, and it also has a lower density. There is some evidence of volcanism on the surface, and also evidence that there was water on the surface. We're seeing some great results coming out of the recent lander on Mars. But one thing you do notice, other than the big cratering events on Mars, is there's this big dichotomy you have in the northern hemisphere, what we call the lowlands, in the southern hemisphere, these much higher elevation terrain. What we're looking at here is just a map of the surface, and the blue colours show that they're low terrain, and red and oranges show that they're higher terrain. So you can see that this real dichotomy, and it's been speculated in recent work that this could even be the result of a giant impact event. Something came in and stripped the surface from the northern half of the planet, and it will land in the southern half of the planet, and that's why we have a much younger surface in the northern hemisphere. So that's just a brief overview of the terrestrial planets. What we want to know is how did we go from planetesimals, things the size of the asteroids in the asteroid belt today, how did they grow from that size up to the active planets that we have today? Well, actually, the key thing here is that we had further collisions between those larger planetesimals. If you remember back to lecture 2, we spoke about how we formed these oligarchs, the largest planetesimals in their population, that grew much more quickly than anything else in the population. And collisions between those oligarchs led, if they were at the right velocities, they could stick together, and that led to the growth of even larger bodies. And so in that way, because of this gravitational focusing effect, we could grow much larger bodies efficiently. And that's the predominant theory of how we formed then these terrestrial planets, just more and more collisions happening in the early solar system. We can test this theory with computer simulations. So we have some colleagues of ours in Arizona who work on this, who have taken a simulation. They've taken a population of planetesimals and add in a few planetary embryos and allow them all to evolve dynamically, their orbits to evolve. And if they come into contact with each other, they'll merge together, and then we can see how things grow and interact in the solar system. We call these simulations n-body simulations because we can add in any number of bodies into these simulations within the limits of your computer. And the way we test these models then is we look to see, do we have the right number of rocky inner planets? So do we have 3 to 4 rocky inner planets in the right kind of orbital distances from the star? And then we can try and determine if our input parameters into these models are correct, and if the processes that we think are forming the planets, if they are correct. In these models, we're assuming that the gas giants have formed earlier than the terrestrial planets. I'll come on in the second part of the lecture to discuss why we think the gas giants formed earlier. But for now, we're just going to assume that Jupiter and Saturn and the other giant planets were already in place before this period of terrestrial planet formation. Just before I go into that, looking at these models in detail, I just want to remind you again of what we mean by orbital eccentricity and inclination. We spoke about this last week. If you remember, the planet's eccentricity is a measure of how elliptical its orbit is. So remember Kepler's third law, or was it the second law? All planets orbit in ellipses around the Sun, with the Sun at one of the two foci, and we can then take a measure of how elliptical that is by looking at the semi-major axis. And the more elliptical something is, the greater this eccentricity number is. And then we have the orbital inclination, so this is the other number that we use to describe the orbit of a planet around the Sun. And the inclination is a measure of the angle between the plane of the orbit of our planet and the plane of the orbit of the Sun, of the Earth around the Sun. So in this movie, what we're going to look at is, on the x-axis, we have the orbital distance from the Sun, so this is our semi-major axis of the orbital ellipse. And we have, out here on the outside, we've got Jupiter sitting out in its orbit at around 5 AU. This measuring on the x-axis is astronomical units, where 1 is the distance of Earth from the Sun. We then have a population of particles here that are going to collisionally and dynamically evolve through time. The red particles, which are kind of behind these overflow particles, there are embryos that they're going to grow into the planets. And then the different colours, the green, the blue, the pink and the yellow, there are planetesimal populations, just coloured by where they start in this simulation. I'm not sure exactly how many we had in here, but typically they run with thousands of planetesimals. As we run this through, you'll see quickly within a few tens of million years, the planetesimals were all kicked up into, this is our eccentricity, into very eccentric orbits, so very elliptical orbits. And within tens to hundreds of millions of years, we formed just a few terrestrial planets, and then within about 100 million years, they actually fall into fairly stable orbits. So I just play that through one more time. So you see our red planets are growing quickly, and we get within around 70, 80 million years, we've got these stable orbits of these terrestrial planets forming in the terrestrial planet region, so between about half and 2 AU. So these simulations, I mean, lots of these simulations run, and they're all kind of stochastic in the way that they run, so that because there's an element of chance whether something collides with something else, the way they do these is they run a whole suite of these simulations and look at which outcomes are more probable. But they have been able to, with these simulations, come up with nice fits to the data, creating the right number of terrestrial planets in the right kind of region. But you'll notice from this that the planetesimals were all kicked up very early into very eccentric orbits. Now what that means is that they'll be on very elliptical orbits around the Sun, where planets are probably on much more circular orbits, and so they'll be crossing each other's orbits very frequently, and that means that we're going to get very many collisions between the planetesimal population and the planets, and we're also going to increase the velocities of those collisions because of those highly eccentric orbits. And what that means is the young Earth, for example, this is what we call the Halian period, because it's almost hellish on the surface. We've got heating coming from all these very high velocity impacts. We've also got heat coming from the radioactive material that would have been present in the young Sun, and so on the surface we've got molten material, and then we get many of these kind of impacts delivering more and more heat as we go through time. We'll talk more about these kind of events when we talk about the Earth in one of the later lectures. So just pause there, that's our kind of summary of how the terrestrial planets formed, how we think they formed just from these kind of collisional events. What we're going to look at over the next few slides, we're going to take a summary of some of the giant planets, and then look at our leading theory for how we think the gas giants formed. So, first of all, just outside the asteroid belt, we have Jupiter, so it's the closest of the giant planets to the Sun. It's 11 times larger and about 300 times heavier than the mass of the Earth. But it has a much lower density. It's around 1/4 of the density of the Earth. And it's thought that it possibly contains, or probably contains, a rocky core around the size of the Earth in the centre of the planet here, and then it's surrounded by this large atmosphere of predominantly hydrogen and helium. Jupiter, even, we can see evidence of impact on its surface. If you remember back to 1994, when the impact of the comet Shoemaker-Levy 9 on the surface, we saw all these marks as a trail of comet debris impacted into the surface of Jupiter. Next up, we have Saturn, which is about 10 times larger than Earth and around 100 times heavier. Very low density, and again, it has an atmosphere of hydrogen and helium, and it's dominated in images by its rings of dust and ice around the planet. And again, this is thought that it has a small rocky core similar to how Jupiter does. But then outside Saturn, we have what we call the ice giants of Uranus and Neptune, which are smaller than Jupiter and Saturn, but still around 4 times the radius of the Earth, and similar density to Jupiter. As I said, along with Neptune, they're what we call ice giants, and they contain more ice in their atmospheres than Jupiter and Saturn. Uranus is a special case in that it rotates on its side, so you can see the rings here are almost vertical here as opposed to Saturn's, which are much more close to the equator this way. And the reason for this is thought that there was another giant impact event which could have knocked the planet onto its side. And as I said, Neptune is similar in composition to Uranus, and also has many ices in its atmosphere, just like Uranus. So in summary, to compare the two populations of planets, we have the small, rocky, dense planets, the terrestrial planets of Mercury, Venus, Earth, and Mars, and then Jupiter, Saturn, Uranus, and Neptune are much larger, much more gaseous. They have these large, dense atmospheres, and much lower density than the range of the terrestrial planets. So really then we want to know how did they form, and why are they so different from the inner planet population. This slide is just to give you an idea of just the difference in size between these planets, just to give you an idea of the scale of Jupiter compared to the scale of Earth and the terrestrial planets. But the way they formed, well, our dominant theory for how we think the gas giants in our solar system formed is what we call the core accretion theory. And now this theory which shows that we think that a core formed rapidly by a two-body collision. So this is the same way that our planetesimals grew into embryos and then planets. So we quickly form this core, and then as that core formed, because it formed so quickly, there's still gas available in the disk, and so that would get attracted to the core by the gravity of the core. And then more planetesimals would form onto this core, and the core would grow, and as the core grows, the gas envelope will grow as the gravity increases. And then when we get to a certain point, we're going to enter a runaway process. But why did the core form so much more quickly for these outer planets than it did for the inner planets? Well, the answer there is there are two reasons, really. First of all, is we're so much further from the sun, the disk has a lot more mass in a given annulus around the sun. In a given ring, there's more mass to be accumulated into planets. And secondly, because we're further from the sun, temperatures are colder, and so we've been able to form ices, we've been able to condense out of the gas. So we have ices such as ammonia and water ice, and these can all go into helping to build up into our solid bodies. So because of these two reasons, if we're outside of what we call the snow line, where ices are able to condense, we can quickly form these cores that go on to form the giant planets. Some simulations have been done of this to give us an idea of the timescale of these different events. And it's shown that the core can actually form quickly in around 500,000 years. And then over the next 6 or 7 million years, we start to accumulate the atmosphere onto the planet. The core doesn't grow that much during that time. When we get to a point, and that takes, as I said, around 7 million years, we're just growing from the feeding zone close to the planet. When the mass of the gas around the planet exceeds the mass of the core, we actually get to a point we call runaway growth, and the planet quickly grows into much greater mass, whereas generally just accumulating a lot more gas onto its surface. And so that's how we think then that the giant planets were able to form that much more quickly than the terrestrial planets, which then, as I said, we then used that in our models of terrestrial planet formation. We assumed that those gas giants were in place a long time before the terrestrial planets formed. And if you remember that the Earth, we think, probably formed in tens of million years, and the cores of the gas giants probably formed in around 500,000 years, so you can get an idea of the different timescales. Now, in the final part of the lecture, I want to go through some of the recent advances that we've had in the field of planet formation, and give you an idea of some of the models that people are running to try and explain some of the open questions that we still have, that we haven't been able to explain fully with just these two simple models. So, some of these open questions that the models don't fully explain. Well, first of all, Uranus and Neptune, in their current locations, it's thought that they probably wouldn't have been able to form fast enough to form the size of planets that they are. The gas at the large distances they are from the Sun are not dense enough to be able to quickly form the planets that we see. A second open question is why the giant planets, why do they all have eccentricities and inclinations that are non-trivial? They're much greater than zero. It's thought that if they form quickly, the gas may have dampened their orbits down to circular and coplanar orbits. And finally, the question of how did the dwarf planets and Pluto form in the Kuiper belt, that the mass of the Kuiper belt is thought to be too small today to have been able to support the growth of these dwarf planets. And the answer actually may lie in orbital resonances. So if you remember from last week when we were talking about the asteroid belt and some of the processes that occur in the asteroid belt, we looked at how an orbital resonance where an asteroid falls into a resonance with Jupiter can affect its orbital properties. And just to recap then, what we mean by an orbital resonance is we mean that in a small number of orbits of our small body, if that falls into sync with one orbit of our large body, which is Jupiter, that could actually give it a small kick to the planet every time it gets close. So if we just run this through, you see that our blue planet here is going to orbit 3 times around the Sun, while Jupiter, our red planet, just orbits once around the Sun. Now, if you imagine every time they line up at this close distance here, Jupiter imparts a small kick to the smaller planet. That can really throw the orbit of that smaller planet out and can have a significant effect on its orbit. Now, the model that I'm going to talk about first is what we call the Nice model. This was named for the observatory in Nice in France, and where it was developed by some researchers. And they found that if Jupiter and Saturn fall into an orbital resonance with each other, we can actually have a big effect on some of the outer planets and the Kuiper belt. So in this simulation, what I'm going to be showing you, as we run this through, it's going to take several hundred million years, but we have, on the inside here, we have Jupiter and Saturn and the ice giants. Their orbits are shown. Jupiter is in red and Saturn in white. The ice giants are in blue and purple here. And then the Kuiper belt, all the objects here are shown in green, just orbiting outside the orbit of Neptune. And we're looking down onto the orbits here, and you can see that they're all interacting. Some of these planets, some of the planetesimals in the Kuiper belt are being thrown out of their orbits, but things are kind of stable for up to 500 million years, and everything's still sitting there nicely, and nothing's really happening. But around 880 million years, what happens in this simulation is that a resonance between Jupiter and Saturn occurs. And when that happens, you can see the dramatic effect that has, not on just their orbits, but on the orbits of everything in the system. So here we come, we're coming up to 880 million years. If you watch what happens as they fall into a resonance, everything explodes into a much wider orbit. You can see even that the orbits of the two, if I run that through again, you can see the orbits of the two ice giants actually exchange places as we get towards the end of the, after that resonance event. So it's an interesting result. We don't have any evidence that that's correct, but in this particular simulation that these works have run, they show that Uranus and Neptune actually change position. You can also see, as that happened, why the mass of the Kuiper belt would be so much smaller than the mass of the Kuiper belt today, and that might explain how we could quickly form in this 880 million years. We could form up to the dwarf planets we see today, but then when we look now, we see there's this much smaller mass of bodies out there, and that would be why we have this kind of difference between the two.
Over what period of time we got this explosive event? What period of time does this take? How many? You're doing hundreds and hundreds of works.
Yeah.
How many orbits does it take?
Oh, it's very quick. I don't know exactly how many orbits, but it happens on timescale of this. It's almost instantaneous, as you can see. Now we're just going to look at the same simulation again, but this time looking at it from the side. So here we have the semi-major axis, so the orbital distance from the Sun. And again, we have Jupiter, Saturn, and now we know that this is going to be Neptune in blue and Uranus in purple. And then on the y-axis, we have the eccentricity. So again, that measure of sort of how elliptical its orbit is. At the moment, you can see how the population of the Kuiper belt, some of these have very eccentric orbits, even in the first few hundred million years. But the outer planets, the giant planets, are all fairly circular in their orbits. Remember what we said, one of the things that our model couldn't explain was why these orbits were so much higher in eccentricity and inclination than we'd expect. We're expecting them to be down here on this kind of low eccentricity orbit. When we get to 880 million years, you'll see what happens to their eccentricities, which you couldn't see in the previous movie. But as we hit that resonance between Jupiter and Saturn, you'll see that their eccentricities are going to shoot up, and that helps to explain then, it's one possible explanation why, here we go, their eccentricities are non-zero eccentricities. And you can see that then this also pushed out Neptune and Uranus. They started here around 10, 15 AU from the Sun, and they ended up around 20 or 30 astronomical units from the Sun. So that again explains how they could form so much larger than we would expect them to form if they formed out in this outer region. So this is a nice model, this is the Nice model, that explains some of these different things, but you have to remember that this is just one particular model. This is one simulation that people have run that seems to match some of our observations. But there's some people who say, well, this is just one model. There could be any other number of reasons why we see these observations, but this is one way that we've been able to explain some of those different observations.
What's in the Kuiper belt?
I'm sorry?
Are those asteroids or that's part of it?
Well, actually, they're similar to planetesimals, but they're probably much more icy than the asteroid belt, because we're out past that snow line. A lot of the solid material will be icy. So it's similar to Pluto, with how icy Pluto is compared to the asteroids. Even though it's similar size to some of the asteroids, it's a lot icier. Okay, so this is then just another figure from that Nice model showing the orbital distance of each of our giant planets is just the minimum and maximum distance they are from the Sun in their elliptical orbits. And you can see to start with, for a long time, they're on these very stable orbits, and then we hit that resonance here at about 880 million years. Jupiter and Saturn don't move too much, they move out a little bit. Jupiter actually moves in a little bit, but Uranus and Neptune you can see switch places and become a lot more elliptical in their orbits, and Saturn as well, a lot more elliptical. So So in summary then, just to say, as we said, Uranus and Neptune probably formed closer to the Sun than they are now, which overcomes the problem that they would have been, there wouldn't have been enough material at the distance that they formed, enough gas to be able to form the size they are. The resonance of Jupiter and Saturn throws all the giant planets into higher eccentricity and inclination orbits, which explain their non-circular orbits. And the Kuiper belt, as I said, the dwarf planets in the Kuiper belt probably formed before we lost all that mass due to that resonance event. And what does this mean for the rest of the solar system? Well, you saw when that resonance event happened, we threw all the planetesimals in the Kuiper belt, they all went in all directions, and many of them actually came in towards the inner solar system. If we look at some of the bodies in the inner solar system, such as the Moon, there's actually evidence, or possible evidence, this is again a disputed thing, but there's possible evidence on the Moon that we see a peak of impact at around 3.9 billion years ago, which kind of matches the kind of event that we see in the NEAS model. They call it late heavy bombardment on the Moon, and there's many kind of impact basins on the Moon that kind of match that timescale. One of them is the basin in Moon. We'll talk more about the late heavy bombardment and some of the processes going on in the Moon when we get to the lecture on the Moon in the coming weeks. One more kind of open question that I want to discuss before the end of the lecture is, why is Mars so small? If you look at the terrestrial planets, Jupiter and Venus and Earth are around the same size, you'd actually expect Mars to be bigger, or around the same size, at least the same size as Earth, or bigger, because it formed further from the Sun, where there was more mass to accumulate into a planet. So there's been this question, kind of, people have been kicking around for a long time, saying, why is Mars so much smaller? It's only around a tenth of the mass of the Earth. And one theory that some of the workers in our Department of Geophysics in the University of Chicago have come up with is they think that actually Mars may have just stopped growing early. Something happened in its history that stopped it growing to a full planet. So actually, what they call a stranded planetary embryo, just its growth was stunted by some process. And here we just have a figure from one of their models that they show. So the time after the solar system birth, they show that the growth of Mars is somewhere in this yellow curve. And so after 2 or 4 million years, its growth actually finished, and it wasn't able to grow into a full terrestrial planet size. And they did this, they looked at the isotopic compositions of Martian meteorites and compared them to our chondritic meteorites, these meteorites that we spoke about last week that show kind of the pristine, unaltered state of the early solar system. And they were able to show then from those isotopic measurements the time that they expected Mars to have stopped growing. But what could cause Mars to stop growing? Well, one theory is what we call the grand Tack theory. There are several theories actually that try and explain this. The one that's gained a lot of prominence recently in the last year or two is the one we call the grand Tack theory. I actually always thought it was because what happens in this theory is that Jupiter moves inwards in its orbit and then back outwards, and I thought it was like a thumbtack moving into a forward and out again. I was actually reading yesterday, they actually say it's because of, it's similar to a sailboat going in and tacking around, that it goes in and out. So it's, whichever way you want to think of it, it's, it could be either, but the theory in this is that Jupiter is going to migrate inwards, a long way inwards, and mix things up in the solar system, and then it's going to move back out. So in this simulation, we're going to be looking at similar kind of movie to what we've been looking at for some of the other models. Here we have Jupiter, Saturn, and Uranus and Neptune. This is going to occur a lot earlier than the NEAS model. So where the NEAS model happened in hundreds of million years later, this is happening in the very early solar system. We also have a population of planetesimals, so we have in red those that formed inside of Jupiter's orbit, and then in blue those that formed outside of Jupiter's orbit. And we have 2 plots here, we have the eccentricity and the inclination. So these are just our 2 measures of the orbits of all these bodies. And what we're going to see in this first movie is Jupiter is going to move inwards towards the Sun, so the Sun is on the left-hand side here, so Jupiter's going to move inwards, and we'll see what happens as that occurs. As it moves inwards, it throws all these bodies on the inside, it kind of pushes them and squashes them towards the Sun, but it also throws some of them outwards past its orbit. Let's run that through again. You can see some of these red bodies are getting thrown past it, some of the blue ones are getting pushed inwards as well. So we're mixing up these bodies in the mixing up all these different populations of asteroids, and Jupiter's kind of coming in. And if we just run that one more time, you'll see that at the same time, after Jupiter moves in, Saturn moves inwards as well. It starts to move in towards Jupiter, if you come in quite quickly. And they think that this movement of Jupiter is probably due to currents in the gas or something. I don't fully understand the reasons behind it, but if Jupiter moved in, that's kind of the processes that it could have. The second movie I'm going to show you, that this is the point we got to after 110,000 years into the simulation. Jupiter and Saturn are very close into the Sun now, around 1.5 to 2 AU from the Sun. And now we're going to see as they start to move back outwards. The reason they move back out is they've fallen into a resonance. So here's that term again, an orbital resonance. They fall into a 3-2 resonance with each other, Jupiter and Saturn. And this actually happens to pull the planets back outwards. And what happens is they go back outwards. Some of these planetesimals are scattered back into the inner solar system and end up back in towards where the asteroid belt is going to end up. See that again, so all the planets are now moving back outwards due to that resonance between Jupiter and Saturn. Now we'll just look at that again, but this time we're going to be looking at top down. So here we've got all those bodies that formed inside of the orbit of Jupiter, then the 4 black rings of Jupiter, Saturn, Uranus and Neptune, and then all the blue population, that's all the planetesimals that formed outside of Jupiter's orbit. And as you can see, first of all, Jupiter moves inwards and it squashes up that belt inside into a very thin orbit. And then Saturn comes in and pulls Jupiter back out. And then we have this population in the centre. It's kind of a mixture of the bodies that formed on the outside and the bodies that formed on the inside of the disk. If you remember last week, we were looking at different classes of asteroids, the Enster-type, Estonian, and Chondritic asteroids, and how they were all, it seemed like there was some pattern that the Enster-type asteroids were towards the inside of the belt, where we think they formed close to the Sun, and the carbonaceous ones were on the outside of the belt because they had more ices. But there was some mixture of those bodies. There weren't a perfect separation of those 3 classes of asteroids. And this is one way we could possibly explain how those different classes got mixed. But also, I came into talking about this model because we wanted to explain why Mars is so small. Well, one of the reasons we think of that is if you watch this model run through it again, if everything gets squashed into the inner solar system and then comes back out, most of our planetesimal population now is only around 1 AU. There's a big gap after you get to the 1 AU, there's kind of an edge in that belt, there's many fewer bodies outside 1 AU. And if Mars was forming outside of that distance, there would have been a lot less mass for it to be able to accumulate onto its surface. And that would lead to the much smaller size of Mars. So again, this is one possible way that we can lead to the smaller mass of Mars. This is just a summary of that model and just to recap. So we started off before the simulation, we've got Jupiter and Saturn, we've got the S-type asteroids, if you like, in the inside, and the C-type asteroids outside of Jupiter's orbit. As we go through, Jupiter and Saturn move in, and we scatter some of these S-type asteroids outwards. And then as Jupiter and Saturn move back out, we mix those in the asteroid belt, so we then have a mixture where we have the S-types towards the Sun, and C-types on the outside. We get kind of a mixture of the two in the centre. There are other scenarios. One of them is called planetesimal-driven migration that could explain the small size of Mars. I'm not going to go into much detail today, but the theory here is that Mars is pushed outwards every time it interacts with one of the planetesimals in the population. It interacts gravitationally. It pushes Mars out slightly and slightly in. Lots of these different interactions slowly push Mars outwards until it leaves the region which is most populated by planetesimals. And again, then, because it's no longer in the region where there's a lot of mass to collide on the surface, that leads to the slower growth of Mars. And at that point, then, I'd just like to summarise what we've spoken about today and finish the lecture. So we've learned that the inner planets grew by just pairwise collisions, similar to the way the asteroids, planetesimals and asteroids grew in the early solar system.
When you're doing this modeling, you've got to start with the mass distribution.
Yep.
And then the same laws would apply in each of these models, wouldn't they? How would they be different?
Well, actually, because there's you can start with many different situations. We don't know what the initial mass was in the solar system. We don't know what the initial orbits of Jupiter and Saturn were. We don't know what the initial orbits of all the planetesimals were.
I understand, but that means you're starting, it's not so much a mechanism difference, but a starting point difference.
Yes, to a large extent, yes, that's true. And the thing is, we don't know what the mechanism is, so people come up with sensible guesses of what we think the initial conditions were, and then allow these to evolve in these different ways. So we don't know, and you can change slightly the physics that are involved in these models, but we don't fully know what the conditions were to start with. So these are just people coming up with models that they think will fit, and then once we have these models, we can examine them and test them more and more But this is the way that we do these. Because we have such limited information about the very early solar system, we can't come up with a solid, we can't say, well, this is what we started with, this is what we ended with, what happened. We have to come up with a guess. I mean, this is what we ended with, but what did we start with? We don't really know. So we just come up with a kind of an educated guess, if you like, of what we think we started with, and then lead through to where we think we finish. So as I said, the inner planets formed by pairwise collisions, the gas giants grew much more quickly because of the extra mass in the outer disk from the condensed ices and the fact that it was in the sun, so its angular region had more mass in it. The cores of those planets grew quickly and then accumulated the large gaseous atmospheres, and they formed much more quickly than the inner planets. And then those outer planets could have significant effects on the inner planets and the asteroid belt as they start to fall into resonance with each other. And next week, what we'll look at is, as I said earlier, we'll start to look at collisional processes. So we'll look at some of the physics behind what happens when two asteroids collide and what are the collateral effects between when those kind of collisions occur. And with that, I'll stop and just say thank you. Yes?
Last week you told us that the gravity of Jupiter was responsible for the lack of formation of the planet, whereas that's mathematical for the predicted. And we couldn't therefore say that always giving Mars and more. I mean, the gravity of Jupiter has the planet of the asteroid or less.
Yeah.
Couldn't the same effect hold in Mars?
It's possible, but I think we're kind of looking at different
Repeat
regions.
the question, please.
The question is, could Jupiter's orbit have affected the growth of Mars? I'm not sure if it could have. But it's a possible model. But, I think we're talking about Mars formed so far from Jupiter that I think that wasn't such a strong effect. Yes.
You mentioned that Mars stopped growing within 2 to 4 million years. What is the zero? That's 2 million years after what?
Yeah, good question. But what is the start of the solar system? I'm going to turn this off because it's making. The question was, what's the starting point? We say Mars formed within 2 to 4 million years. What do we count as the time zero, if you like? And that's a big question that we don't really know. I mean, we can take the time that the gas dispersed from the disk as our time zero. We can take several different points. When did the CAIs form? These are some of the earliest solid bodies that we had in the solar system. We don't have a good handle of what time zero is, but I think in this model we're talking probably about from the dispersal of the gas from the disk. And we're talking about 2 million years after that.
What is the temperature at the snow line that separates the terrestrial and the ice?
The question is, what's the temperature at the snow line? I don't know the answer to that. It wouldn't just be the freezing point of water because we're at a different pressure, but I don't know the exact temperature that we're talking about there. I mean, it'll be minus several hundred probably degrees, but I don't know exactly what. Yes.
With the runaway growth from the gas giants, are they still growing?
No, because the gas is all dispersed now. I mean, they were growing while we still had gas in this disk around the sun. Once they got to the point that gas all dispersed, that would then lead to the hole today.
But they're still getting collisions, or not?
There will still be a few collisions, but the mass of the things that are colliding with them now is so small compared to the mass of the planets that they're not growing anymore.
How frequently do Jupiter and Saturn go into a resonance state?
The question is, how frequently would Jupiter and Saturn go into resonance? And I think that's something that we just don't know the answer to. I don't think they're going to go in. They're kind of fallen into these stable orbits, so they're probably not going to get into a resonance again anytime soon. How often they did it during the history of the solar system, that's something we don't know, because all we have is what their orbit is today. But we can come up with these models that suggest if they fell into these resonances, these are the effects that happen. But we can't say for certain they would happen every X number of years. We just can't.
So you're going to speculate what might happen whatever the next time?
I'm not sure that has been speculated. It may have been. I don't know of any work. Yes, in fact.
Is there anything between the Nice models and the Grand Tack models that sort of exceed each other? I know that they're completely different time scales, but is there any reason that they're in competition with each other?
The question is, is there anything that happens between the Grand Tack model and the Nice model? Why are they in competition? I don't think they're actually in competition with each other. They could, they could happen. They could both happen if you like, or it could be a combination of the two, or even the planetesimal migration, driven migration, that could also be included. It could be a combination of all these effects. At the moment, these are sort of early work. People have just looked at one of the effects in isolation. There hasn't yet been anyone done a model where they kind of combined all the effects to try and build a grand theory of everything, if you like. But there's no reason why they have to be separate. Yes?
Is it possible during the planet building process that some of the early planets might have been knocked out of the solar system altogether? Do these models take that into account?
The question is it possible during this period that some early planets could have been knocked out of the solar system? And yes, I mean, if you look at those simulations of our forming planets and planetesimals, you can see some of the planetesimals get right into very high eccentricity orbits. Now, if they go past an eccentricity of 1, they fall into, rather than being in an ellipse around the sun, they'll fall into a parabola or a hyperbola and actually go out of the solar system. So it's possible, maybe for the larger bodies it's less likely, but it is possible, definitely for the smaller planetesimals. Maybe they do get into orbits, to either planet-crossing orbits or out of the solar system together. Now, if they fall into a planet-crossing orbit, all manner of things could happen. They could collide with one of the planets or get thrown into a completely different orbit or thrown into the sun. So all that can happen and is accounted for.
What is it about the gas giants when they reach that point where the gas mass is greater than the core that causes the runaway growth? What is the dynamic?
The question is, what's the dynamics that cause the runaway growth in the gas giants after the gas reaches a higher mass than the core? I'm not sure exactly what the physics is in that. I think it's just that the gravity gets that much larger that it can pull in gas from further afield. But I don't quite get that. I'm not 100% sure. Yes?
When the giant planets constrict their orbits, they would have to speed up.
Yep.
How does that happen there? Where would they get the energy to speed around?
The question is, as the giant planets move inwards towards the center of the solar system, they will speed up. And your question is, where would they get the energy to speed up? Well, it's not that they're getting extra energy. If you remember our discussion of angular momentum from the early lectures, the angular momentum is a product of its mass, its radial distance, and the velocity. So as the radial distance decreases, the velocity has to increase. So the momentum is actually the same around the sun. It's just because we've decreased the radius, we have to increase the velocity. Yes?
So in your simulations, when the Jupiter and Saturn get close to the sun, do they ever collide together?
The question is, do Jupiter and Saturn ever collide when they get close to the sun? I don't know the answer to that. There are, with these simulations in this paper that the work presented for the Grand Tack model, what they do is they don't just run one model, they run lots of models because they're stochastic in the model. The events are all kind of random depending on what collisions occur when and what happens. So this is just one result from a whole suite of simulations they ran. Whether in some cases things collide, I don't know. I don't think it's common for them to collide. I think they kind of keep each other apart because they're mills. But I don't know if it does ever happen, and I don't know what would happen if it did.
What is the time relationship between when the sun formed, or as they say, switched on, formation of planets? Was the sun already formed and all this?
Yeah, the question is, what's the time relationship between the sun forming and the planets forming? And yeah, the sun formed before any of this happened. But the disk of gas and dust that formed around the sun was still evolving as the giant planets formed.
But the sun had stopped growing.
It may have still been growing a little bit as that gas disk evolved, but I think the majority of the sun had already formed. But the giant planets had to form while we still had that gas present. That's how they were able to grow into the gas giants. If they formed after the gas had dispersed, then they wouldn't.
I was going to ask the question, could Jupiter and Saturn sometime collide? But I was going to ask, what would be the possible effects for Earth that ever happen?
If Jupiter and Saturn collided, what would be the effect on Earth?
Right.
I'm not sure that's something we would ever need to worry about. We wouldn't be around to find out. I don't know the answer that would happen. I mean, it would obviously throw our orbit into some completely different orbit, and that would have effects on the. If we didn't get consumed by all the impact, all the debris from that impact, if that didn't come and affect our planet, then our orbit would change, the atmosphere would change, the temperature and the surface would change everything. But I don't know.
Uranus rotates on its side. Is one of its poles always facing the sun, or what's the surface temperature? What implications does that have on the temperature?
I don't know the answer to that. I'm not 100% sure. The question is Uranus rotating on its side, does one surface always face the sun? And I actually don't know. But even if one side did always face the sun, because it's a gaseous atmosphere rather than a solid surface, even if it is always the same pole facing the sun, there's going to be enough movement in that gas that it's not one section always getting radiation. But I don't know the full answer to what the temperature is on the actual.
You said, why does it rotate on its side? One thing might have been an impact. Any other possible explanation?
Question is, are there any other possible explanations for Uranus rotating on its side? I don't know. I assume there are some other possible explanations. The impact is one of the leading theories, but I don't really know anything about the other.
If Uranus's tilt was the result of a collision, why would the ring also have changed its orientation?
Good question. I guess because the ring would come from the rotation of all material around it. So if the body is rotating in that direction, then maybe
So it's like ejected from the...
It could be ejected from the collision. Yeah. I don't know. I haven't studied Uranus.